What if the secret to saving humanity was hidden in the first moments of the universe? What if objects smaller than atoms, yet more massive than mountains, held the key to solving our energy crisis and unlocking the mysteries of existence itself? This is the story of primordial black holes, the forgotten cosmic discoveries that could transform civilization as we know it. Throughout history, humanity's greatest breakthroughs have emerged from the most unlikely places. The ancient Greek philosopher Democritus, gazing at the endless dance of dust motes in sunlight, conceived of atoms, invisible building blocks of reality that wouldn't be proven for 2 millennia. Medieval alchemists, in their seemingly futile quest to transmute lead into gold, unknowingly laid the groundwork for modern chemistry and atomic theory. And Galileo, pointing his crude telescope at Jupiter's moons, shattered humanity's geocentric worldview forever. Each of these discoveries shared a common thread. They revealed that the universe operates on principles far stranger and more wonderful than we had dared imagine. And now, in the 21st century, we stand on the precipice of another such revelation, one that reaches back to the very birth of the cosmos and forward to the salvation of our species. The key lies in understanding objects so bizarre, so counterintuitive, that they sound like science fiction, yet they may be the most abundant form of matter in the universe. To understand primordial black holes, we must first journey back to the universe's violent birth. 13.8 billion years ago, all of existence was compressed into a region smaller than a proton, yet containing the seeds of every star, every planet, every atom that would ever exist. Imagine, if you can, the entire observable universe with its 100 billion galaxies, each containing hundreds of billions of stars, all squeezed into a space so small it would make an atom look like a cathedral. The temperature of this primordial fireball? 10 to the 32nd power degrees Kelvin. To put this in perspective, the core of our sun burns at a mere 15 million degrees. The surface of the hottest stars reaches 100 million degrees. But the infant universe? It was a trillion times hotter than any star that has ever existed. At such temperatures, matter as we know it could not exist. There were no atoms, no molecules, not even protons or neutrons. Instead, there was a seething ocean of pure energy, where particles and antiparticles danced into existence and annihilated each other in violent flashes of light. Then, in the first trillionth of a trillionth of a trillionth of a second, something extraordinary happened. The universe underwent a process called cosmic inflation, a period of exponential expansion that defies our everyday understanding of physics. Space itself expanded faster than the speed of light, growing from subatomic to cosmic proportions in less time than it takes light to cross a proton. But here's the crucial detail. This expansion wasn't perfectly uniform. Like cream being poured into coffee, there were fluctuations, tiny variations in density that would have profound consequences for the future of the universe. These primordial fluctuations were quantum in nature, ripples in the very fabric of space-time itself. Imagine the surface of a pond, disturbed not by stones or wind, but by the fundamental uncertainty principle that governs reality at its smallest scales. In most regions of the early universe, These quantum fluctuations were relatively gentle, tiny variations that would eventually grow into the cosmic web of galaxies we see today. But in some rare regions, the fluctuations were extreme. Here, matter and energy were compressed to such extraordinary densities that they formed what physicists call overdense regions. When cosmic inflation ended, these overdense regions faced a moment of cosmic reckoning. Gravity, that most familiar yet mysterious of forces, began to assert its dominion. In ordinary circumstances, the expansion of the universe would overcome gravitational collapse. But these weren't ordinary circumstances. The density in these regions was so extreme that gravity won. Matter collapsed in on itself with such violence, such unstoppable force, that it punched holes in the fabric of space-time itself. These holes became the universe's first black holes, primordial black holes, born not from the death of stars, but from the chaotic birth of the cosmos itself. Unlike the black holes we're familiar with today, those stellar giants born from the collapse of massive stars, primordial black holes came in an astounding variety of sizes. The smallest could be lighter than a paperclip, yet contain the mass of an entire mountain. Others might weigh as much as our sun, compressed into a sphere no larger than a city. And the largest, they could dwarf even the supermassive black holes that lurk at the centers of galaxies today. But here's where the story becomes truly remarkable. These primordial black holes weren't just cosmic curiosities. They were time capsules, preserving within their event horizons the conditions that existed in the universe's first moments. Think of them as cosmic DNA, carrying information about the universe's birth that we could never access any other way. Every primordial black hole is a direct link to the Big Bang itself, a fossil from the moment when the laws of physics were still being written. The ancient philosophers spoke of the music of the spheres, the idea that celestial bodies created a harmony as they moved through space. They couldn't have known how prescient this concept would prove to be. Modern physics has revealed that the universe does indeed have a song, gravitational waves that ripple through space-time whenever massive objects accelerate. And primordial black holes? They might be the universe's oldest instruments, still playing melodies from the cosmic dawn. In 2015, when the Laser Interferometer Gravitational Wave Observatory first detected gravitational waves, it opened an entirely new window into the cosmos. For the first time, we could hear the universe singing. The waves we detected came from the collision of two black holes, each about 30 times the mass of our sun. But some scientists began to wonder, could these black holes be primordial? Could we be listening to echoes from the universe's birth? The implications were staggering. If even a fraction of the black holes we're detecting are primordial, it would revolutionize our understanding of the early universe. It would confirm that the cosmos underwent a period of incredible violence and creativity in its first moments. More importantly, it would suggest that primordial black holes might be far more common than we ever imagined. And if they're common, they might solve one of cosmology's greatest mysteries. For decades, astronomers have known that the universe contains far more matter than we can see. The stars, planets, and gas clouds that populate the cosmos account for only about 5% of the universe's total mass and energy. The rest, It's invisible, detectable only through its gravitational effects. We call it dark matter, and it remains one of the most profound puzzles in modern science. What if the answer has been hiding in plain sight? What if dark matter isn't some exotic particle we've never discovered, but something far more familiar? What if it's black holes, primordial black holes, scattered throughout the cosmos like seeds from the universe's violent birth? This possibility has captured the imagination of physicists around the world. Consider the elegance of the idea. Instead of invoking mysterious new particles that exist beyond the standard model of physics, we could explain dark matter using objects we already know exist. Black holes are real, their properties are well understood, and their gravitational effects match exactly what we observe from dark matter. The ancient Chinese philosopher Lao Tzu wrote that the sage does not attempt anything very big, and thus achieves greatness. Perhaps the universe follows similar principles. Perhaps the solution to our greatest cosmological puzzle isn't found in the exotic, but in the elegantly simple. But the story of primordial black holes extends far beyond solving the dark matter mystery. These cosmic time capsules might hold the key to understanding the very nature of reality itself. In the 1970s, Stephen Hawking made a startling discovery. He showed that black holes aren't perfectly black. They emit radiation, a faint glow that carries away their mass and energy. The smaller the black hole, the brighter it glows and the faster it evaporates. For stellar mass black holes, this Hawking radiation is negligible. They would take longer than the age of the universe to evaporate completely. But the smallest primordial black holes? They would be brilliant beacons, shining brighter than stars as they consume themselves from within. This radiation isn't just heat and light. It's information, quantum information about the fundamental structure of space-time. By studying the Hawking radiation from primordial black holes, we might unlock secrets about quantum gravity, the theory that would unite Einstein's general relativity with quantum mechanics. It's here that the ancient meets the cutting edge in the most profound way. The Vedic texts of ancient India spoke of cycles of creation and destruction, of universes being born, evolving, and dying in endless cosmic rhythms. Modern physics suggests they might have been more right than they knew. If primordial black holes exist in sufficient numbers, they could play a crucial role in the universe's far future. As the cosmos expands and cools, as the last stars burn out and the universe enters its final dark age, primordial black holes might be the last sources of energy. Their Hawking radiation could power civilizations for trillions upon trillions of years, long after every star in the sky has died. But the implications go even deeper. Some theoretical physicists have proposed that our entire universe might have emerged from the interior of a primordial black hole in a higher dimensional space. In this view, every black hole might contain within it the seeds of a new universe, a new Big Bang waiting to unfold. If this is true, then primordial black holes aren't just fossils from our universe's past. They're cosmic wombs, nurturing new realities within their event horizons. The Hindu concept of Brahma, the creator deity who dreams universes into existence, takes on new meaning in light of modern cosmology. But we're getting ahead of ourselves. Before we can harness the power of primordial black holes, Before we can use them to unlock the secrets of existence, we must first prove they exist. And that's where our story takes an exciting turn. Around the globe, scientists are deploying increasingly sophisticated instruments to hunt for these cosmic ghosts. Gravitational wave detectors like LIGO and Virgo are listening for the characteristic songs of colliding primordial black holes. Space-based telescopes are scanning the gamma-ray sky, searching for the telltale signatures of evaporating black holes. And particle accelerators are probing the fundamental laws of physics, seeking clues about the conditions that would have created these objects in the first place. The search for primordial black holes has become one of the most exciting frontiers in modern astrophysics. It's a detective story on a cosmic scale, with clues scattered across 13 billion years of cosmic history. Every new discovery brings us closer to answering fundamental questions about our place in the universe. Are we alone? How did the cosmos begin? What is the nature of space and time? And perhaps most importantly, how can we ensure the survival and flourishing of our species in an indifferent universe? The ancient Stoic philosophers taught that we should focus on what we can control and accept what we cannot. But they also believed in the power of reason and knowledge to transform both ourselves and our world. In many ways, the search for primordial black holes embodies this philosophy. We cannot change the fact that we live in a universe governed by forces far beyond our immediate control. But we can seek to understand those forces, to decode the cosmic DNA written in the language of mathematics and physics. And in that understanding, we might find not just intellectual satisfaction, but practical wisdom. The technologies we develop to detect primordial black holes, the theories we create to explain their properties, the international collaborations we forge to study them, all of these efforts expand our capabilities as a species. They remind us that we are not passive observers of the cosmos, but active participants in the grand story of existence. We are the universe becoming conscious of itself, reaching back to touch its own origins, reaching forward to shape its own destiny. As we conclude this first part of our journey into the world of primordial black holes, we stand at a threshold. Behind us lies the comfortable world of everyday experience, where objects behave predictably and time flows in one direction. Ahead lies a realm of quantum uncertainty and gravitational extremes, where the very concepts of space and time break down and reality reveals its deepest mysteries. The primordial black holes we've explored today are more than just theoretical constructs or astronomical curiosities. They are invitations to think bigger, to dream bolder, to imagine possibilities that stretch the boundaries. In the depths of space, trillions of miles from Earth, two primordial black holes are spiraling toward their ultimate destiny. Born in the universe's first moments, they have wandered the cosmos for over 13 billion years. Now, locked in a gravitational dance of death, they emit ripples in space-time itself, gravitational waves that carry the story of their ancient origins across the universe. On Earth, in a facility that looks more like a cathedral than a laboratory, scientists have built the most sensitive measuring device ever created. The Laser Interferometer Gravitational Wave Observatory can detect changes in distance smaller than 1/10,000th the width of a proton. When those gravitational waves from the colliding black holes finally reach our planet, traveling at the speed of light, They cause LIGO's arms to stretch and compress by this infinitesimal amount. And in that moment, humanity hears the universe singing, a song that began before our solar system was even born. This is the new age of multi-messenger astronomy, where we don't just observe the cosmos with light, but listen to it with gravitational waves, taste it with neutrinos, and feel it with cosmic rays. It's an age where the boundary between astronomy and archaeology has blurred, where every detection is a glimpse into deep time, and where the hunt for primordial black holes has become one of the most exciting quests in modern science. The story of our modern search for primordial black holes begins with a puzzle that has haunted astronomers for nearly a century. In the 1930s, Swiss astronomer Fritz Zwicky was studying the Coma cluster, a vast collection of galaxies bound together by gravity. Using the newly developed technique of measuring galactic velocities through spectroscopy, Zwicky made a shocking discovery. The galaxies in the cluster were moving far too fast. According to his calculations, they should have escaped the cluster's gravitational pull eons ago, scattered across the cosmos like leaves in a hurricane. Yet there they were, held in gravitational embrace by some invisible force. Zwicky concluded that there must be vast amounts of unseen matter in the cluster, matter that revealed itself only through its gravitational effects. He called it Dunkel Materie, dark matter. For decades, astronomers hoped this was just an anomaly, a quirk of that particular cluster. But as they peered deeper into space with increasingly powerful telescopes, the evidence mounted. Galaxy after galaxy, cluster after cluster, showed the same pattern. The visible matter, the stars and gas clouds that shine in the night sky, was like foam on the ocean's surface. Beneath it lay vast, invisible depths. By the 1970s, astronomer Vera Rubin had clinched the case. Her careful observations of galaxy rotation curves showed that stars at the edges of spiral galaxies were orbiting far too quickly to be held in place by the visible matter alone. The implications were staggering. The universe, it seemed, was mostly made of something we couldn't see, couldn't touch, and couldn't understand. The search for dark matter became one of the greatest detective stories in science. Physicists proposed exotic particles, theoretical constructs with names like axions, neutralinos, and sterile neutrinos. They built detectors deep underground, shielded from cosmic rays, waiting for the faint signature of a dark matter particle colliding with ordinary matter. They constructed massive particle accelerators, hoping to create dark matter particles in high-energy collisions. Decades passed. The detectors remained silent. The accelerators found no trace of these hypothetical particles. Meanwhile, a different possibility was quietly gaining momentum. What if dark matter wasn't some exotic new particle at all? What if it was something we already knew existed, something that had been hiding in plain sight all along? What if dark matter was black holes, specifically primordial black holes, scattered throughout the cosmos like cosmic seeds from the universe's violent birth? The idea was elegant in its simplicity. Black holes, by definition, are invisible. They reveal themselves only through their gravitational effects, exactly like dark matter. They're made of ordinary matter, compressed to extraordinary densities, not exotic particles that exist beyond our current understanding of physics. And if they formed in the early universe during the chaotic moments after the Big Bang, they could be distributed throughout space in exactly the pattern we observe for dark matter. But there was a problem. For primordial black holes to account for all of dark matter, they would need to exist in enormous numbers and in a very specific range of masses. Too small, and they would have evaporated by now through Hawking radiation. Too large, and we would have detected them through other astronomical observations. The sweet spot, according to theoretical calculations, lay in a narrow window of masses, roughly between that of an asteroid and a small planet. Black holes in this range would be stable against evaporation, yet small enough to have escaped direct detection. They would be cosmic ghosts, influencing the motion of galaxies and galaxy clusters through their gravity, but remaining invisible to even our most powerful telescopes. This is where the story becomes truly exciting, because the technology to test this hypothesis was just coming online. The first detection of gravitational waves in 2015 opened an entirely new window into the universe, one that could finally reveal the presence of primordial black holes. When two black holes spiral into each other, they create a characteristic pattern of gravitational waves, a cosmic chirp that encodes information about their masses, spins, and orbital dynamics. By analyzing these signals, scientists can determine whether the colliding black holes formed from the collapse of massive stars, as we traditionally expect, or whether they might be primordial relics from the universe's birth. The differences are subtle but detectable. Primordial black holes might have different mass distributions, different spin properties, or different clustering patterns than their stellar-formed cousins. Each gravitational wave detection is like a forensic analysis of a cosmic crime scene, revealing clues about the nature and origin of the objects involved. Since 2015, LIGO and its European counterpart Virgo have detected dozens of black hole mergers. With each new detection, scientists scrutinize the data for signs that some of these black holes might be primordial. The mass ranges of the detected black holes have been surprising. Many are heavier than astronomers expected stellar black holes to be, falling into what was previously considered a mass gap. This has led some researchers to wonder, could we be detecting primordial black holes right now without even knowing it? The possibility has energized the scientific community. If even a fraction of the black holes detected by LIGO are primordial, it would be the first direct evidence for these ancient objects. It would confirm that the universe underwent a period of incredible violence and creativity in its first moments, violent enough to forge black holes from pure energy. But gravitational waves are just one part of the modern hunt for primordial black holes. Across the electromagnetic spectrum, from radio waves to gamma rays, astronomers are searching for their signatures. The smallest primordial black holes, those with masses similar to asteroids, would be evaporating through Hawking radiation right now. As they consume themselves from within, they would shine like cosmic beacons, emitting high-energy particles and gamma rays. The Fermi Gamma Ray Space Telescope and other high-energy observatories are constantly scanning the sky, looking for point sources of gamma rays that can't be explained by known astrophysical processes. Any unexplained gamma-ray source could potentially be an evaporating primordial black hole, a cosmic firefly burning out after 13 billion years of existence. Meanwhile, radio astronomers are using a different approach. They're looking for gravitational microlensing, the subtle bending of light that occurs when a massive object passes between Earth and a distant star. If primordial black holes exist in the numbers required to explain dark matter, they should occasionally drift in front of background stars, causing them to brighten temporarily as their gravity focuses the starlight like a cosmic lens. The search for microlensing events has become a high-tech treasure hunt. Automated telescopes scan millions of stars every night, looking for the telltale signature of a dark object passing in front of them. Each detection must be analyzed carefully. Was it caused by a primordial black hole, or by some other dark object like a brown dwarf or rogue planet? The answer lies in the details. The duration and shape of the brightness curve can reveal the mass and distance of the lensing object. Primordial black holes would create very specific patterns, distinct from other astronomical phenomena. So far, several promising candidates have been detected, objects with masses in the range expected for primordial black holes. But proving their primordial nature remains challenging. The hunt has also gone underground, quite literally. Deep beneath the Earth's surface, in abandoned mines and specially constructed laboratories, scientists have built exquisitely sensitive detectors designed to catch dark matter particles. These detectors, cooled to temperatures colder than outer space and shielded from cosmic radiation, wait patiently for the faint whisper of a dark matter interaction. If dark matter consists of exotic particles, these detectors should eventually spot them. But if dark matter is primordial black holes, these underground vigils will continue in silence. This creates an interesting paradox. The absence of detection in these underground experiments could actually be evidence for primordial black holes. Sometimes, in science, what you don't find is as important as what you do. The search has also extended to space itself. The James Webb Space Telescope, humanity's most powerful eye on the cosmos, is being used to peer deeper into space and further back in time than ever before. If primordial black holes exist, they might have played a role in the formation of the first stars and galaxies. By studying the most distant and ancient cosmic structures, Webb might reveal the gravitational fingerprints of these primordial giants. Meanwhile, theoretical physicists are using supercomputers to simulate the early universe, modeling how primordial black holes would form and evolve over cosmic time. These simulations are like time machines, allowing us to witness the universe's first moments and understand how tiny quantum fluctuations could grow into massive black holes. The computational challenges are staggering. Simulating the formation of primordial black holes requires modeling physics across an enormous range of scales, from the quantum realm to cosmic structures. But the results are illuminating. They show that under certain conditions, primordial black holes could indeed form in the numbers needed to explain dark matter. They also reveal new ways these objects might reveal themselves to our instruments. One of the most exciting developments in the search for primordial black holes comes from an unexpected source: ancient light. The cosmic microwave background radiation, The afterglow of the Big Bang carries within it subtle patterns that encode information about the universe's earliest moments. If large numbers of primordial black holes formed in the early universe, they would have left their mark on this ancient light. By analyzing the cosmic microwave background with unprecedented precision, scientists can place constraints on how many primordial black holes could exist. The Planck satellite and other missions have mapped this ancient radiation in exquisite detail, revealing that the early universe was remarkably smooth and uniform. This smoothness places limits on how many primordial black holes could have formed. But the story is not over. Future missions will map the cosmic microwave background with even greater precision, potentially revealing subtle signatures that current instruments cannot detect. The hunt for primordial black holes has also inspired new theoretical frameworks. Some physicists propose that these objects could solve multiple cosmic mysteries simultaneously. Not only could they explain dark matter, but they might also account for the supermassive black holes found at the centers of galaxies, objects so massive they shouldn't have had time to grow since the Big Bang. If some primordial black holes formed with masses millions of times that of our Sun, they could have served as seeds for these galactic giants, growing through accretion of surrounding matter over billions of years. The implications extend even further. Some researchers suggest that primordial black holes could be connected to other cosmic puzzles, such as the matter-antimatter asymmetry of the universe or the nature of cosmic inflation itself. In this view, primordial black holes aren't just passive relics of the early universe. They're active players in cosmic evolution, shaping the structure and composition of the cosmos over billions of years. The search for these objects has also fostered unprecedented international collaboration. Teams of scientists from dozens of countries work together, sharing data and expertise in the common quest to unlock the universe's secrets. The LIGO-Virgo collaboration involves thousands of researchers from around the world. The Fermi Gamma Ray Space Telescope team includes scientists from multiple nations. And the theoretical work on primordial black holes draws on expertise from cosmologists, particle physicists, and mathematicians across the globe. This collaborative spirit reflects the fundamental nature of the challenge. Understanding primordial black holes requires bringing together insights from the smallest scales of quantum mechanics to the largest scales of cosmology. It's a quest that pushes the boundaries of human knowledge and technological capability, demanding new instruments, new theories, and new ways of thinking about the cosmos. As we stand on the threshold of potential discovery, the ancient Greek concept of eureka, the joy of sudden understanding, feels more relevant than ever. Each gravitational wave detection, each gamma ray observation, each theoretical breakthrough brings us closer to answering one of the most profound questions in science. What is the universe made of? The hunt for primordial black holes represents more than just an astronomical quest. It's a testament to human curiosity and ingenuity, our drive to understand our place in the cosmic order. Whether these ancient objects hold the key to dark matter, or whether they remain forever hidden in the cosmos shadows, the search itself has already transformed our understanding of the universe and our place within it. In our final segment, we'll explore how the discovery of primordial black holes could revolutionize not just our understanding of the cosmos, but our future as a species, offering new sources of energy and perhaps even the key to our long-term survival in an ever-expanding universe. Imagine a future where humanity's energy needs are met not by burning fossil fuels or splitting atoms, but by harnessing the power of objects born in the universe's first moments. A future where black holes, those cosmic devourers of light and matter, become our greatest allies in the quest for unlimited clean energy. This isn't science fiction. It's the logical conclusion of our growing understanding of primordial black holes and their potential to revolutionize human civilization. As we stand at the crossroads of climate change and energy scarcity, the ancient wisdom traditions speak of finding strength in unexpected places. The Taoist concept of Wu Wei teaches us that the greatest power often comes from understanding and working with natural forces rather than fighting against them. Perhaps nowhere is this principle more applicable than in our relationship with black holes, objects that represent the universe's most extreme manifestation of gravity and space-time curvature. What seemed like cosmic monsters, devouring everything in their path, may actually be the key to ensuring our species' long-term survival and prosperity. To understand how primordial black holes could save civilization, we must first grasp the scale of humanity's energy challenge. Every second, our planet receives about 174 petawatts of solar energy, more than 10,000 times our current global energy consumption. Yet despite this abundance, we continue to struggle with energy scarcity, environmental degradation, and the looming threat of climate change. The problem isn't the total amount of energy available, but our ability to capture, store, and distribute it efficiently. Solar panels and wind turbines, while important steps forward, still depend on Earth's variable weather patterns and the day-night cycle. Nuclear fission provides consistent power but creates radioactive waste that remains dangerous for thousands of years. Fusion power, long promised as the ultimate solution, continues to elude practical implementation despite decades of research and billions of dollars in investment. But what if the solution lies not in Earth-based technologies, but in the cosmos itself? What if objects formed in the universe's first moments could provide clean, abundant energy for millions of years? This is where primordial black holes enter our story as potential saviors rather than cosmic curiosities. Unlike their stellar mass cousins, the smallest primordial black holes are actively evaporating through Hawking radiation, converting their mass directly into energy according to Einstein's famous equation E=mc². A black hole with the mass of a mountain, compressed into a sphere smaller than a proton, would radiate energy at a rate of 10 to the 16 watts. To put this in perspective, that's roughly the same as the total power output of all the world's nuclear reactors combined. From a single object no larger than an atomic nucleus. The ancient alchemists dreamed of the philosopher's stone, a legendary substance that could transmute base metals into gold and grant eternal life. In many ways, evaporating primordial black holes represent the ultimate philosopher's stone, transmuting mass directly into pure energy with perfect efficiency. Unlike nuclear reactions, which convert only a tiny fraction of mass into energy, black hole evaporation converts 100% of the mass into radiated energy. It's the most efficient power source theoretically possible in our universe. But how could humanity possibly harness such exotic objects? The answer lies in a concept that sounds like science fiction but is grounded in solid physics: artificial black holes. If we could create microscopic black holes with precisely controlled masses, we could, in principle, build power stations that operate by feeding matter into these holes and collecting the resulting Hawking radiation. The physics is straightforward. A black hole with a mass of about 10 to the 11 kilograms, roughly the mass of a large mountain, would have a lifetime of about 1 year before completely evaporating. By continuously feeding it small amounts of matter, we could maintain its mass at a stable level, creating a controlled fusion reactor that operates not through nuclear processes, but through the fundamental structure of spacetime itself. The engineering challenges, admittedly, are staggering. Creating artificial black holes would require concentrating enormous amounts of energy into incredibly small regions of space. Current particle accelerators, even the most powerful ones like the Large Hadron Collider, fall short of the energy densities required by many orders of magnitude. But this is where the discovery of naturally occurring primordial black holes could change everything. If these objects exist in the numbers suggested by some theories, we might not need to create artificial black holes at all. We could capture and utilize primordial ones. The concept of black hole capture and utilization draws inspiration from some of humanity's greatest engineering achievements. Just as we learn to harness the power of falling water with dams and hydroelectric plants, or capture the energy of moving air with wind turbines, we might learn to capture and control primordial black holes. Imagine space-based collection systems, vast networks of gravitational sensors that could detect approaching primordial black holes and guide them into containment facilities. These cosmic power plants could be positioned at Lagrange points, those gravitationally stable regions between Earth and the Moon, or between Earth and the Sun. The energy collected could be beamed back to Earth using microwave transmission, or used directly in space to power massive orbital installations and interplanetary missions. The implications extend far beyond solving our immediate energy crisis. With access to the enormous power output of primordial black holes, humanity could undertake projects that currently seem impossible. We could power massive atmospheric processors to reverse climate change, extracting carbon dioxide from the atmosphere and converting it into useful materials. We could desalinate the world's oceans, providing fresh water to every corner of the planet. We could power vertical farms and synthetic biology facilities, creating abundant food without depleting natural ecosystems. The energy abundance would enable us to break free from Earth's gravitational well, powering spacecraft capable of reaching other star systems in reasonable timeframes. But perhaps most importantly, primordial black holes could provide the energy foundation for what futurists call a Type 1 civilization, a species capable of harnessing all the energy available on its home planet. The concept of civilization types, proposed by Soviet astronomer Nikolai Kardashev in 1964, provides a framework for understanding the long-term trajectory of intelligent species. A Type 0 civilization, which is roughly where humanity stands today, uses only a fraction of its planet's available energy. A Type 1 civilization harnesses all the energy that reaches its planet from its star. A Type 2 civilization captures the entire energy output of its star. And a Type 3 civilization controls the energy of an entire galaxy. Currently, humanity ranks at about 0.7 on the Kardashev scale. We're approaching Type 1 status, but we're not there yet. Primordial black holes could accelerate our progress dramatically, providing the energy density and reliability needed to make the transition to a Type 1 civilization within decades rather than centuries. The ancient Hindu concept of the Kalpa describes vast cycles of cosmic time, periods of billions of years during which universes are born, evolve, and die. Modern cosmology has revealed that our universe may indeed be cyclic, expanding and cooling until all the stars burn out and only black holes remain. In this far future, trillions of years from now, primordial black holes might be the last sources of energy in a cold, dark universe. Civilizations that learn to harness their power could survive long after every star has died, powered by the slow evaporation of these cosmic time capsules from the universe's birth. But the benefits of primordial black hole technology extend beyond mere energy production. These objects could also serve as tools for fundamental physics research, allowing us to probe the deepest mysteries of reality. The Hawking radiation emitted by evaporating black holes carries information about the quantum structure of space-time itself. By studying this radiation in detail, we could unlock the secrets of quantum gravity, the theory that would unite Einstein's general relativity with quantum mechanics. This isn't just academic curiosity. Quantum gravity might reveal new physical principles that could revolutionize technology in ways we can't yet imagine. Just as our understanding of electromagnetism led to radio, television, computers, and the internet, a complete theory of quantum gravity might open up entirely new technological possibilities. We might discover how to manipulate space-time directly, creating artificial gravity for space habitats or even opening shortcuts through higher dimensions. We might learn to create stable wormholes, enabling instantaneous communication and travel across vast cosmic distances. The economic implications of primordial black hole technology are equally staggering. Energy currently represents one of the largest sectors of the global economy, worth trillions of dollars annually. If primordial black holes could provide abundant, clean energy at marginal cost, it would fundamentally reshape the global economic system. Industries that are currently energy-intensive and expensive, such as aluminum production, synthetic fuel creation, and atmospheric carbon capture, could become economically viable on a massive scale. The cost of space travel could plummet, making it economically feasible to mine asteroids, establish lunar colonies, and terraform other planets. But perhaps more importantly, abundant energy could help solve the problem of global inequality. Many of the world's poorest regions lack access to reliable electricity, limiting their economic development and quality of life. Primordial black hole power stations could provide clean, abundant energy to every corner of the globe, lifting billions out of poverty and enabling unprecedented global prosperity. The path from our current understanding of primordial black holes to practical energy applications will require breakthroughs in multiple fields. We need advances in gravitational physics, exotic matter manipulation, magnetic confinement, and radiation shielding. We need new materials capable of withstanding the extreme conditions near black holes, and new computational methods for predicting their behavior. We need international cooperation on a scale never before attempted, bringing together the world's best minds to tackle humanity's greatest challenge. But if history teaches us anything, it's that human ingenuity has a remarkable ability to turn theoretical possibilities into practical realities. The transistor, invented in 1947, seemed like a mere laboratory curiosity. Today, billions of transistors power the smartphone in your pocket. Nuclear magnetic resonance was an esoteric physics phenomenon until it became the foundation for MRI machines that save lives every day. GPS satellites depend on Einstein's theory of general relativity, a theory that seemed utterly abstract when it was first proposed. The journey from scientific discovery to technological application often takes decades, but each step builds on the previous ones, creating a cascade of innovations that can transform civilization. We're currently in the early stages of this process with primordial black holes. The theoretical foundation has been laid, the observational search is underway, and the first tentative steps toward practical applications are being explored. Leading technology companies and government research agencies are already investing in related technologies. Advances in fusion power, quantum computing, and space exploration are creating the technological ecosystem that could eventually support primordial black hole utilization. The search for primordial black holes has also inspired new educational initiatives and international collaborations. Universities around the world are establishing programs in gravitational physics and exotic matter research. Young scientists are being trained in the interdisciplinary skills needed to tackle humanity's greatest challenges. The next generation will grow up with a deep understanding of gravitational physics, quantum mechanics, and cosmology, preparing them to turn today's theoretical possibilities into tomorrow's practical solutions. But perhaps the most important impact of primordial black hole research lies not in its practical applications, but in its effect on human consciousness and perspective. The ancient Greek concept of the sublime describes the feeling of awe and wonder that comes from contemplating something vastly greater than ourselves. Primordial black holes embody this sublime quality. They connect us directly to the universe's birth, reminding us that we are not separate from the cosmos but part of its ongoing evolution. They challenge us to think on cosmic timescales, to consider the long-term survival and flourishing of our species across millions of years. They inspire us to work together, recognizing that the challenges and opportunities ahead are too great for any single nation or organization to tackle alone. In many ways, the quest to understand and harness primordial black holes represents humanity at its best. Curious, creative, collaborative, and committed to building a better future for all. It embodies the same spirit that built the pyramids, mapped the oceans, reached the moon, and decoded the human genome. As we stand on the threshold of potentially discovering these cosmic time capsules, we're reminded that the universe is far stranger and more wonderful than we ever imagined. The objects that seemed most alien and threatening, black holes that devour light itself, may actually be our salvation. The energy released in the universe's first moments, preserved in primordial black holes for billions of years, may be the key to powering our civilization's next great leap forward. Whether or not primordial black holes ultimately prove to be the dark matter we seek, or the energy source we need, the search for them has already expanded our understanding of the universe and our place within it. It has pushed the boundaries of human knowledge and technological capability. It has inspired new generations of scientists and engineers. And it has reminded us that in the vast cosmos, filled with wonders beyond imagination, anything is possible for a species bold enough to dream and determined enough to explore. The forgotten cosmic discovery that could save civilization may not be forgotten much longer. The hunt continues, and with each passing day, we move closer to answering one of the most profound questions ever asked. Can the universe's most extreme objects become humanity's greatest allies? The answer may reshape our understanding of reality itself and secure our species' future among the stars.